Today we're looking at reciprocal functions, but before we can do that, let's just consider what a reciprocal really is. In the past, you might have called it a multiplicative inverse, and you might remember it as something to do with flipping a number upside down. Now, by definition, when you multiply a number by its reciprocal, you get 1, okay? And that's the same whether you're calling it a reciprocal or a multiplicative inverse, same thing. So to think about what 2's reciprocal would be, what number do we need to multiply by here? Well, 2 lots of a half is 1. But also it makes sense that if you're needing an answer to be 1, you'll need a 1 on the top of a fraction, and whatever number you have here, you'll need to have that number on the bottom so that when you multiply them, those numbers would cancel. So the idea is that, yes, you can say I can find a number's reciprocal by just doing 1 over the number. Great method. You can also think of it as flipping a number upside down. Now, that works well with fractions. What about numbers that don't look like fractions? If you consider that 2 is really 2 over 1, then if we flip that, we get its reciprocal. It's important to note that when you flip a number upside down, a positive number will still be positive. A negative number will still be negative. That flipping doesn't change the sign. So that's the first important point. Then we need to consider that a really large number is going to have a really tiny reciprocal, and vice versa. So to give you some examples here to get the idea of it, in case you haven't seen this before, a number like 2 has a reciprocal of a half, and we can see why that works. A number like 3/4, we flip it upside down, we get 4/3, but to explain why it works, 1 over 3/4, we could actually write as 1 divided by 3/4, and we know that when we're learning to divide, that's probably where you've come across this term before, instead of dividing, we multiply and we flip the second number. In other words, we use its multiplicative inverse. And that's probably a method you've been using to divide fractions for years. So if we have a really large number like 1,000,000, then its reciprocal will be 1/1,000,000th. A really tiny number like 1/1,000,000th will have a really large reciprocal like 1,000,000. Now, if we keep on going with these extremes, we can say that infinity would have a reciprocal of 1 over infinity. Now, obviously we can never actually reach infinity. So this number is not ever going to be 0, but it's going to get mighty close. It's going to approach 0. And you can see why that happens. As the number on the bottom of a fraction gets bigger and bigger and bigger, the fraction itself is going to approach 0. But when we have 0 and we try and tip it upside down, what's happening? Well, 1 divided by 0 is something that we can't do. Our calculator can't work it out. We say that it's undefined. So these two really are quite special reciprocals that are going to help us a lot when we start to graph. And there's special notation that we need to learn now to explain what happens when we find the reciprocal of infinity or negative infinity, or when we try and find the reciprocal of 0. So this is the notation that we use. We say as x is approaching infinity, in other words, we're getting larger and larger and larger numbers, 1 over x, or x's reciprocal, is going to approach 0. That's because a really large number has a really tiny reciprocal. But infinity is a positive number, and so we're going to approach 0 from above. And this is how we write it. We put a little positive there to show that we're approaching 0, but we're still in the positive numbers. It's just a tiny, tiny positive fraction. Whereas if x is approaching negative infinity, imagine what it will be. It's a negative number, but it's a long way to the left on the number line. Then 1 over x is still going to be a negative number. So even though it's approaching 0, it's approaching negative from below, which means it's a tiny, tiny fraction, but it's a tiny, tiny negative fraction. Similarly, we can say that as x is approaching 0 from above, in other words, it's a tiny, tiny fraction, but it is positive. We can say that 1 over x is going to approach infinity, positive infinity. Whereas when x is approaching 0 from below, it is actually negative. So when we take its reciprocal, sure, it will be a huge number, but it will be a negative huge number. It'll approach negative infinity. Now, the use of the arrows here instead of equal signs is important because we can never actually reach infinity. We can just approach it. So if we're never actually going to reach infinity, well, we're not actually going to reach 0 either. We're just going to get mighty close. And that's the case in all of these situations. Now, all of these sorts of situations lead to asymptotes on our graphs. Now, there's 2 skills that you need to have when you're graphing reciprocal functions. The first is you need to be able to sketch a reciprocal function when we give you the equation of the original function. Now, that's what we're going to have a look at here. You also need to know how to sketch a reciprocal function when you're just given a graph of a function, possibly when you don't even know its equation. So we'll have a look at that next. Now, the reciprocal of any function, y equals f of x, is either written like this, which is probably more familiar to you, 1 over whatever it is, and we've just defined that that's what reciprocals really are, so that should be no surprise. Or we could see them written this way. Now, we haven't done a lot of work with negative indices yet this year, but soon we'll do more, and you'll be more familiar with the fact that when you raise something to the power of -1, it's exactly the same as writing a fraction with 1 over that exact same thing raised to a non-negative version of that same power, which in this case would just be 1. So you can see it written either way, and they mean the exact same thing. Work with the one that you're comfortable with. Now, if you know the equation of a function, then it's really quite simple to find the equation of the reciprocal function. You just write 1 over, and then you put whatever equation you've been given. And hopefully you'll know how to graph that one. So here's an example. We are going to sketch y equals x minus 2 and its reciprocal function. Now the line y equals x minus 2 should be nice and straightforward for you to graph. Well, you can see that it's in gradient intercept form. So it's got a y-intercept of -2 and it's got a gradient of 1. That means it goes up at a 45-degree angle like that. So I've drawn it here in blue. It goes through y equals -2 and x equals 2 and heads on up like that. Now, I've written the formula of the reciprocal of it first so that I can have a look at that and think about how to graph it. I've literally just put 1 over whatever I had in the original function. Now, we've already looked at how to graph hyperbolas, so this should be fairly straightforward to say it's a basic hyperbola that instead of looking like our normal one that has its asymptotes on the x and y axis and has those two sort of arms like that, and we know that positive ones sit in these two quadrants, negative ones sit in the other two. So it's one of these ones. The one on the top just tells me how big its waist is, and in fact it's always good practice to label a point on one of the arms, and I can see here that one of these points would be for something like y equals 1 over x. I'd have the point 1, 1 here, and -1, -1, and I can tell because the x and the y value need to multiply together to make 1, or 1 divided by 1 equals 1. So I can quickly and easily see what this graph looks like. But this one has got a translation of 2 units. Has it been moved to the left or the right? It's been moved to the right, hasn't it? We're remembering that x minus 2 moves it towards the positive numbers. So I've gone ahead and sketched it here in red, and I can see that its asymptote, instead of being on the y-axis, would now be moved across 2, and so it would now be sitting here at x equals 2, so I've drawn that in. Moving it crossways doesn't change the horizontal asymptote, so that's still going to go this way. And then I've gone ahead and just sketched in the basic shape of those two arms. Now I reasoned that I already knew this point here, 1, 1. So if I move it across 2, I'm going to know that point still, it's going to be 3, 1, isn't it? So this point here is going to be 3, 1. And I can double check that that actually does lie on both the lines. It looks like the intersection, doesn't it? Even on a rough sketch like this. Sure enough, when x is 3, 3 minus 2 is 1. So that lies on my straight line. And when I sub in 3 for x here, I've got 3 minus 2, which is 1 on the denominator, and 1 over 1 is 1. So sure enough, here's my intersection of 3, 1. What else would I need? I could potentially find this intersection over here, although that's a little bit more hard work. All I've got to do is sub in x equals 0, and I'm going to say it's 1 over -2, so that's minus a half. So my graph wasn't exactly perfect there. It needs to probably come up a little bit steeper, and that point there I could label as -0.5. So I've got intercepts, I've got the intersections of the two lines, and I've graphed the function and its reciprocal function together. Now, a few things here that we can notice, just some basic truths. As one of these graphs gets towards really big numbers, and when I say it's getting big, I mean the function is getting big, and I therefore mean y is getting big. As it gets really tall, the other one gets short. But if one of them's positive, so is the other. Okay, and we can see here that as this one gets really big, the other one gets small. As one's negative, so is the other one. And here, as we get really large negative numbers, we get really small negative numbers, and vice versa.